Hello everyone. In this lecture, we are going to study about the next part of the chapter gravitation. So firstly, we are going to discuss some common observation that we observed in our day-to-day life. So it is our common observation that all the material objects have a tendency to be attracted towards the earth. Any object thrown up fall down towards the earth. Similarly, it is very tiring to go uphill than going downhill. So it was Galileo who recognized the fact that all bodies, irrespective of their masses, are accelerated towards the earth with constant acceleration. He made a public demonstration of this fact. He tried to find out the truth by doing various experiments. Since the earliest of time, a seemingly unrelated phenomena like the observation of stars, planets, and their motion have been the subject of attention in many countries. Ptolemy proposed a model for planetary motion, and this model was geocentric model. According to this model, the objects like stars, the sun, and the planets were supposed to revolve around the earth in circular path. In his model, Earth was supposed to be stationary and was taken as the center of the universe. He put forward the technique to describe the motion of the planets. The planets were said to be moving in circle, with the center of circles themselves moving in larger circles. The next model is a heliocentric model. It is also the more elegant model in which sun was the center around which the planets revolve. After that, the Copernicus also proposed a model in which planets revolved in circle around a fixed central sun. At the same time, Galileo and the Tycho from the Denmark spent his entire lifetime recording observation of planets. The data compiled by him was analyzed by his assistant Kepler, and then he concluded the new laws for the planetary motion. The first law is known as law of orbits. This law states that every planet revolves around the sun in elliptical orbit, with sun situated at one of the foci, means center of this elliptical orbit. As the ellipticity of orbit is quite small, so we can treat it as a circular orbit. This law was a deviation from the Copernican model, and as it is clear from the figure, ABCDA is the elliptical orbit followed by a given planet with the sun at the focus F1. There is also second focus of the elliptical orbit that is named as F2. So as from the figure, there are the two axes. One is a major axis, second one is a minor axis. AC is a major axis and BD is a minor axis. Here are 2 points. One is capital A, another one is a point capital C. Point A is closest to the sun, so this is known as a perihelion. Perihelion is a point in the orbit of a planet at which it is closest to the sun, and the point C is the farthest from the sun, so this is known as aphelion. So for a circle, the two foci of the ellipse merge into one, and the semi-major axis becomes the radius of the circle. So now second law, which is known as the law of areas or law of areal velocity, states that the line that joins any planet to the sun sweeps equal area in equal interval of time. That is, areal velocity of planet around the sun remain constant. Why areal velocity? Because if any planet cover up equal area in an equal interval of time, then as per the formula of the velocity, area means distance over time. It means it is covering the velocity. So it means that the areal velocity of a planet around the sun remains constant. And we can say that this law comes from the observation that planets appear to move closer when they are farther from the sun than when they are nearer to the sun. So first of all, look in the figure. Here are the 4 points, the point A, point B, here is a point C, and at the last point D. Suppose a planet takes the same time in going from position A to B as is taken by it in going from position C to D. Then according to Kepler's second law, areas are equal. So the area ABS is equal to area CDS. As the Kepler law says that the line that joins any planet to the sun sweeps out equal area in the equal interval of the time. So hence, because of the definition of the Kepler's second law, we conclude that area ABS is equal to area CDS. As the areas are equal, the length of the path CD is more than that of path AB. Away from the sun, its velocity decreases, and as it approaches the sun, its velocity increases. Also, this law is based upon the law of conservation of angular momentum. Law of time period states that the square of the time period of revolution of a planet around the sun is directly proportional to the cube of semi-major axis of its elliptical orbit around the sun. So we can say that according to this law, if capital T is the time period of revolution of a planet around the sun and small r is the semi-major axis of its elliptical orbit around the sun, then according to Kepler's third law, T square is directly proportional to R cube. Smaller the orbit of a planet around the sun, shorter is the time taken by it to complete one revolution and vice versa. Now next one is a numerical that is based upon the Kepler's third law, and the statement is calculate the period of revolution of Jupiter around the sun. The ratio of the radius of Jupiter orbit to that of Earth orbit is 5 and the period of revolution of the Earth is 1 year. So things are given. First of all, that is we have to calculate the time period of revolution for the Jupiter. So for that we denote the time period of Jupiter by Tj, and also the ratio of the radius of Jupiter orbit and the Earth orbit is given 5, and we apply the Kepler's third law. T square is directly proportional to R cube. Rearrange the terms. We know 1 is equal to T square upon R cube. So write the equation, write the formula of the Kepler's third law for Jupiter as well as for the Earth. Then we know that both these terms must be equal to the 1, so we can compare the terms, and rearranging we can find the value of the Tj square, then solve the square root, then we get the final answer, that is 11.18 here. So try to solve such other numericals which are based on the Kepler's third law. So this is for today. Hope you like this video. Thank you and have a nice day.